I have to apologize. I am totally out of place in this place. When this invitation came to me, I actually asked him several times, are you sure you're not making a mistake? I don't belong in this group because I've never presented anything to non-statisticians in my life. I've never done it. I've always been with statisticians and sometimes with computer scientists, but I've never, ever, ever, ever presented in a cloud of non-statisticians. So forgive me if the language I use is entirely different from what you've known in your life. Okay, so because what I'm going to say is unlike anything anyone is going to present in this workshop or conference, okay? So bear with me and just be patient. I'm going to try to keep it simple. I'm going to try to keep it very intuitive so that you're not bored. I'm not known for boring people. That much is true. So you should not be bored. So what I'm going to do right now is, it belongs to statistical machine learning. I can give you a summary of my presentation. If you've ever heard of bagging, boosting, or random forest, then you'll feel comfortable. Then you will recognize some of the terms I'm going to use. This is a summary. After my talk is over, you will go home and know that if somebody has a lot of different estimator of the same function, instead of selecting one of them, he can just combine them together in some clever way to reduce the prediction error. The assumption here is that the individual candidates called function estimators, I'm going to call them base learner. That's how they call them in Answerable Learning. And I'm going to assume that they come to me with a little bias, but maybe large variance. And I'm going to hope that the combination of them is going to reduce their variance so that the resulting prediction error is as small as possible. I'm not going to be showing you any theoretical results. I'm going to show you intuition. All right? So this is what it looks like. What do I call ultra-high dimensional space? It's a very fancy word, simply to refer to situations where the number of observation is far smaller than the number of variables measured. We call that a wide design matrix. When the design matrix is wide in regression analysis or classification, the problem becomes what numerical analysts call an underdetermined system. An underdetermined system violates what we call the Adamar conditions of well-posedness, right? Because you need a solution to exist, you need it to be unique, and you need it to be stable. In this case, that solution cannot be unique. Therefore, you got to do something about it. One of the ways to deal with this problem is called selection. Oh, sorry, I don't know. How does it work? Oh, this way. Okay. So I'm going to consider this problem in a sim-less way. I'm going to imagine that I can do classification and regression in a sim-less manner. The ultra-high dimensionality in this case will just have to do with the fact that I have more P's than I have N. One of the ways to solve this, an example of this problem is a problem that I collected at my university in Rochester. I'm glad to be here because it's extremely cold at my home. So when I see myself wearing a vest in February, I wonder if they should not call the psychiatrist for me. But in this case, I am not in Rochester, so I'm safe. So there's no medical doctor coming after me. Ultra-high dimension. I collected some problems for the so-called speaker accent recognition because I have a lot of people from different places in my community, and we wanted to, solve a tiny little binary classification problem to distinguish the U.S. accent from the non-U.S. accent. And I'm trying to demonstrate to my students that this problem is inherently weird compared to the other problems they've solved in their lives. Why? Because if I had to solve it in time domain, unfortunately, I'm going to have a 550,000 dimensional input space, which is untenable. Right? It's totally untenable. If you're trying to use traditional method, it won't even start. You can't use logistic regression on that, except maybe you do some kind of projection into some frequency domain and have a nice dimensionality. But that's not what we're talking about here. We're talking about situations where traditional data sets of interest to me came to me from the field of DNA microarray data analysis, and they wanted me to perform classification on this data. Now, if you want me to perform classification on this data set, this is what I call the poverty of the data. The poverty is represented by the fact that the ratio of N over P is less than 1. So if that ratio is less than 1 by a lot, I call extreme poverty, okay? Scarcity of data, right? Which contrasts with the traditional setting where the logarithm of my covariance matrix looks pretty nice. in some sense, okay? So this is the setup where I am. And traditionally in machine learning, what you want, you can imagine somebody wanting to choose a single model, right? So in other words, if I give you a collection of models that are solving a problem, I'm trying to classify this guy as US accent versus non-US accent, or I'm trying to classify these people as cancer versus non-cancer. What I want is, I may have a plurality of models. There's a huge variety of them. In our field, we have the so-called Bayes classifier. This is the theoretical best classifier that you can imagine. In practice, nobody ever builds the Bayes classifier. This is used for theorem. This is used for characterizing a particular model that you build. You build a model, you want to know, if I had the truth, how would this model compare to the truth? If I had the absolute best, how would this model compare to the absolute very best? Okay? That's not what I'm doing today. I'm giving you a very simple, intuitive technique for solving a problem whereby I won't be giving you a theorem that compares my algorithm to the Bayes risk. I won't be doing that. I won't be doing that. Okay? So I will be giving you a heuristic. I'm struggling with this. Okay. So this is the key to what I'm going to be presenting to you. This is the key here. The key is this picture. Anyone who's been exposed to statistical machine learning has seen this picture 1 billion times. As many times as you open a book that deals with statistical machine learning, you will see the picture that shows you the so-called bias-variance trade-off. The bias-variance trade-off has something to do with the interplay between the bias and the variance of an estimator. I'm going to construct different Bayes learners. In my case, I won't be worried if their variance is large, because by combining them, I'm going to offset the largeness of the variance by actually doing some clever little tricks. Okay, so this is the picture that summarizes what I'm going to be talking about. Now, there's an alternative to what I'm going to be presenting to you. The alternative to what I'm going to be presenting to you is something called regularization. Regularization, and you are all mathematicians, you understand from Tikhonov that when you have an ill-pass problem, one of the best ways to approach the ill-posedness is to use regularization. The problem is ill-pose. One of the ways to offset that problem is to constrain it. To constrain it in order to isolate a family of possible solutions. Now, in the case of trees, which are very formidable Bayes learner in the machine learning community, we don't have the luxury of having a nice objective function so that we can regularize it in the way that Tikhonov wants us to do it. So we have to find a way when we have these trees to be able to say, these trees are unstable. How do I combine many of them in order to offset this trend, this high variance of the estimators? Okay. Now, these are some of the techniques that I use to solve this same problem. So support vector machine is traditionally well used for problems when you have p larger than n, because inherently it could always deliver a solution whether p is larger than n or n is larger than p. I hope I haven't lost you yet, but I already gave you the summary of my presentation. You may leave now because I already told you exactly what it is that I was going to talk about. Now, this is where I need my technique. The method I'm going to explain to you is used when my Bayes learner, what I'm calling a Bayes learner is a simple mapping. I'm trying to construct a classifier. That's what I want to do. I have an input space that has p dimension in it, but I have only n observation with n less than p. If I try to construct one of the most commonly used techniques known as logistic regression, I won't be able to do that because the matrices and the operations needed for constructing the estimators will not run. They won't work. They won't work for the simple reason that, in fact, I may be making this more complicated than it is. If you're trying to solve a regression analysis problem, which I hope, even though you're not a statistician, you should know regression analysis. I'm sorry, you should. If you don't, then I'll be very disappointed. So I'll be extremely disappointed. In fact, I will be shocked. So if you have this incredible object here that you probably have written that gazillion times in your life, if p is larger than n, you cannot solve that problem. That's not possible because x transpose x is singular. You can't do that. You can't do that. So what happens then is that you do something called random subspace learning. What is that? It's a very fancy word to say instead of suffering through this problem where I cannot construct a single solution, I am going to randomly choose a number of variables such that n will be larger than the q that I choose. Unfortunately, because I have to do that randomly, I can't do it only once. I have to do it repeatedly in order to somehow search the model space. Because the idea here is that I'm searching a model space because I don't really know which of the variables is actually responsible for the mapping. So, because I'm trying to construct this mapping, I'm trying to go from this input space to this output space. It turns out that the dimension of this input space is larger than I care. And so what I'm going to do, I'm going to play a game. I'm going to try to construct many subset of this with Q that is way less than P. And because I'm going to do that randomly, I have to construct a multiplicity of them and combine them in some clever way so that the resulting estimator is at least as good as the best of each one of them. Okay, so that's what I'm doing. Nothing more. That's what I'm doing here. All right, good. All right, so I'm going to avoid using this. This is one of the techniques that you could use to solve this problem. You could solve this problem by doing the so-called regularization a la Tikhonov. So if you use regulation a la Tikhonov, you can solve this problem in some way. You can even combine this, the so-called ridge regression, which is, you could refer to that as an L2 penalization. You can combine this L2 regularization with the L1 regularization in something known famously now as the elastic net. Okay? Somebody tell me why I'm struggling with this. It doesn't work for me. Have to look at the errors I'm having. Okay, now it works now. So this is the gist of my presentation. So what I'm going to do then, I'm going to do something that is called the ensemble learning. Okay, the ensemble learning here is going to assume that somebody gave me many different simple learners for my problem. Maybe say capital L of them, okay? And then you give me capital L of those, and I can imagine combining them in some ways, like just getting a linear combination of these base learners. So I'm going to get a linear combination of this base learner, but I have to construct them in such a way that the resulting F, the guy that is a combination of all of them, has some nice properties. The question number one is, how do I choose those base learners? The second question is, do they come from the same family? Because I can imagine constructing a homogeneous ensemble or a non-homogeneous ensemble. And I can also imagine one of the keys here is the way that this guys is combined, I have to combine them in such a way that they do not hurt each other. You know, I don't want them to be antithetic. So I have to do something in such a way that the resulting combination is somewhat close to uncorrelated. And I have to find ways to combine the weights and so on. Okay? So that's the gist of my presentation. And the gist of this presentation relies on how is the base learner constructed. This is the key. The key to this algorithm is that I need many different base learners. Why? I need many base learners because I'm using a random assignment. So when you have a random assignment, you want to make sure that by the time you average them, that you have searched your model space carefully enough so that you have a good representation of the mapping from the input space to the output space. The first step, I'm going to borrow it from random forest. It's called bootstrapping. So I'm going to resample my data with replacement, and that resampling with replacement will give me a plurality of data sets, because each time I perturb my data set, I get a new estimator. Each time I perturb my data set, I get a new estimator. Second step is the step that we bring into this algorithm, is that I'm going to come in and randomly select, without replacement, a number Q of the variables out of the P that are very large. Okay? And then once I do that, I'm going to create then my random subspace. And after having created my random subspace, I'm going to call my learning algorithm. This learning algorithm could be anything. It could be a Bayesian algorithm. It could be some maximum likelihood. It could be some, empirical risk minimization. It doesn't matter. So this is the general framework of what it is that I'm doing. And the key to what I'm doing is that I'm cleverly using these weights in such a way that the resulting estimators are compellingly good. That's what I'm doing. So once I finish that, I construct my ensemble, and I can just aggregate my functions in a clever way. So where's the key? The key in this is that the construction I did is such that the resulting estimator is always better than the best of the individual learners. That is the algorithm. Now, I don't show you the proof to that, but the resulting estimator that I have is always less, has an error, a training error, average training error that is less than the best of the individual guys. Because otherwise, this exercise is useless. Because first of all, it's going to be more computationally expensive than somebody just building one single estimator. So in other words, if you're building one single estimator and doing better than somebody who's aggregating them, then the aggregation is pointless. Now, the question that nobody asks is, what is special about this then? What is special is that my second step, which is one of the steps that differentiates this from boosting and random forest, is this step here. The second step here, the cleverness, well, I'm not saying clever because I did it, but it turns out to be clever. I have to say that because it's true. So it's computationally cheap. It frankly costs you nothing at all. So I'm not trying to be an idiot here. I'm just telling the pure truth. So it turns out that the estimator we construct enjoys this very nice property that this correlation between the individual learners tends to be extremely low. And when that correlation between the learners is extremely low, if you look at this expression very carefully, imagine in the limit, if these guys are totally uncorrelated, that is, this psi is equal to 0. If this psi equal to 0, it means the variance of my resulting aggregate only depends on the individual variance of this machine and the number of machines that I build. So in other words, if I have a large budget of computing, say capital L could be 1 million, then I can just make that L very large, and the result is that my variance is going to become so low that if my bias is low, I'm eating my cake and having it back. This is magic. And that's almost dangerous. Then people start running away from me as a man who does juju. Right? I know I was born in Cameroon, but I don't do juju in mathematics. I do something else, right? So it's very interesting. No, seriously, I'm almost literally joking, but I'm telling the pure truth here. And I might say that, I'm going to say that emphatically, that what we do is going to push this guy close to 0. As a result, all we need to do is to build many of these base learners. Because even if this sigma square is large, if L is very large at the infinity of L, I'm having a variance that's going very low. So if my base learners were all near unbiased, I'm building a formidable machine. So that is the claim, all right? So that's the claim. And now I'm open for people challenging that claim. So that's what it is. So how do I do it? This is the cleverness. I'm going to choose the variables based on a very stupid, simple rule. This is the rule. Consider the p variable, and the p could be 10,000. Like in macroarray, p is 500,000, 10,000, and stuff like that. Imagine that I can find out for each of the genes its ability to separate cancer from non-cancer. I call that the individual predictive strength of variable j. Suppose I consider that individual strength alone. Then I can construct a weighting system, like a multinomial distribution for the variables, that is based a priori simply on the individual strength of each of the variables xj. Now, at first, when I had this thought, I thought, no, Ernest, it won't work. Don't do it. And then I say, what about? Try it. Try it and see. So when you try this and you realize that, I have so many of them. I can use R squared, I can use the F statistics, I can use so many things. If I'm using a classification problem, I can just look at the ability to separate different classes by one single variable. That's called analysis of variance, right? I can do analysis of variance under the Gaussian assumption of the variable. But even if I lose the Gaussian assumption, I can use Kruskel-Wallis. So in other words, I can very cheaply, outside of the loop of my algorithm, create a distribution in the input space for selecting the variables randomly. And that's where the random subspace comes in. That now what I can do when I create, for instance, if I'm just solving a regression problem, in 10,000 dimensions. I can just say, let's consider 10,000 variables and calculate the individual R-square for each of the variables, and just calculate some simple weighting scheme, and choose each of the variables a priori. Each time I'm selecting a random subspace, I choose it according to the weight, the individual strength. Then if you're Bayesian, you can imagine somebody calculating the posterior weight of that variable. But at least you have a nice a priori. You have a very reasonable prior distribution on the input space. Okay? So, almost out of time. That's fine. So, okay, very simple. This is a simple example here. I mean, you can ask me questions about this if, like I said, I told you earlier, I don't dream that any of you cares about this at all. If you don't, fine, I won't be offended. This is a miracle that I'm here. Right? I tried to challenge Matt not to bring me here. He said, Ernest, come and present your work. Some people might be interested. Maybe. I don't know. So anyway, so this is an a priori distribution on the weights that is pretty interesting. You see, for instance, this variable has a greater chance than that one. This is not rocket science. So and so we have done this, and then there's so many different schemes, and we have studied different aspects of each of them. And what happens is that in some cases, believe it or not, in many cases, we have examples where we beat random forest on some important task with this simple, idiotic tool. So, in other words, if you've been around this setup of machine learning, you know that to beat random forest or boosting is a formidable task, okay? Because these are very incredibly interesting algorithms. So this picture is just showing you what I say, that if your ensemble is not better than a single learner, then it's not worth it. As you can see here, if you consider a homogeneous ensemble where the base learners are all trees, obviously if you bag the trees perfectly, you should always have an error that's less than the individual tree itself. So this is the average test error for bag the tree. This is the average test error for boosting. This is the average test error for random forest. So this is just demonstrating that, you know, the ensemble, the aggregate should be better than the individual. How about us? So what we do now, I'm just showing here a bunch of little examples where we actually use this little algorithm on a variety of data sets. So this is a toy problem. On this toy problem, I'm trying to demonstrate two things. That the combination of the base learners has to be clever. If it's not clever, then you result into a disaster. But if it's clever, like in the adaptive weights that we're using, then you end up with a learner that has very low variance. This box plot is an indication, the thinness of this box plot is an indication that this machine is quite stable, and, well, even more stable than random forest in this case, which is very unusual. This is pretty good. This is an indication that this does better. And then we have that in many different other machines where this technique does quite reasonably. Right now, at this point, we're working on the theoretical justification of some of the aspects why the weighting scheme that we use is achieving the kind of performance that it does achieve. And last but not least, this is just for different data. These are just benchmark data set that anyone who works in the statistical machine learning or data mining, you've seen the people when they create new algorithms, they tend to compare them on these tasks. They're well known. This one is a formidable task that's usually extremely hard. And so basically, we show here that we construct uncorrelated learners, and also we finish by showing that as a byproduct, and this is an incredibly important activity when people work on ultra high dimension, is explaining which of the dimensions matter. This is almost like by way of interpretability in a setup where you have a non-parametric system, because indeed this ends up being totally non-parametric because you're combining models, so you lose entirely the interpretability of a single model. But in this particular case, free of charge, and I mean this truly free of charge, this algorithm will generate the importance of each of the variables because it's actually sampling them, right? So it's sampling them. This is almost like a form of a posterior inclusion probability as used in the Bayesian setup of each of the variables. Okay, so this is the merit of this algorithm. So what have I told you today? Today, I came here to share with you that there is a lot of ultra-high dimensional data out there, tons of it. Tons of it, in image analysis, in video analysis, in DNA, in medical science, in text mining. A lot of data sets are ultra-high dimension in the sense that you have more variables measured than you have observations. But then, there's so many different ways of approaching prediction for those data sets. One of the ways, which I still respect tremendously, is regularization. You can construct regularized learners for solving those problems. What I managed to do today to you guys is to give you an alternative in the family of the so-called ensemble learning, namely aggregating models in random subspace, by providing, I really hope, a very clever way of choosing individual variables in the input space. Thank you.